Hi, this is Dr. Neff, and I want to give you some background information on solutions so that we don't have to take the time to cover all of it in class. So, first of all, a solution is what's known as a homogeneous mixture. And the picture here really exemplifies what a homogeneous mixture is. You can't tell that there's more than one component. It all just looks like there's one phase there, but there really is something dissolved in that solution. And so we typically say the solute dissolves in the solvent. And we can be pretty technical about those two different components. The solute, like I said, it's the part that dissolves in the solvent, but technically it's the component present in the smaller amount. And so that makes the solvent the component present in the larger amount. And we can make a solution of any of the phases of matter. We could have a solid in a liquid, a solid in a gas, a solid in a solid. And so the solid in a liquid, that's something that we're all familiar with. That would be like salt and water. Solid in a gas, that's like natural gas in native stone, so just in the ground. And then the solid in a solid, that's what an alloy is. So something like brass, that's a combination, a solution of two different metals together. So more terminology includes words like soluble, insoluble, and again, we can be kind of generic with these terms. Soluble just means that it will dissolve. But you can also get really, really specific, and I'll do that in just a minute. Insoluble means that it won't dissolve. But both depend on the solvent, of course, and the solute. So then we can get much more specific and talk about the solubility, which is how much of a specific solute will dissolve in a specific solvent at a specific temperature. And you can look up solubility limits. They're tabulated for a lot of different substances. We've already in class talked about the idea of dissociating compared to just dissolving. And specifically, ionic salts dissociate when they dissolve in water. And so they go from being an extended crystal solid lattice to being the separated ions, aqueous, surrounded by water floating around in solution. So it's a very big difference. But molecular solutes just dissolve. And we talked about this last week in the lab that we did. That just means that they break away from each other, break away from their neighbors, and become surrounded by water. So that would be something like ethanol. It's a liquid on its own, but I can dissolve it in water. It's still ethanol. It's just that now the separated molecules are surrounded by water molecules. So last week talked about the idea of like dissolves like, which means that polar solutes dissolve best in polar solvents. And the same thing for nonpolar solutes and solvents. And we talked about predicting solubility based on IMFs. And you should be really comfortable with this. Looking at something like sodium chloride in water, we would predict that that's going to dissolve. Specifically because, like I said, it breaks up into the component ions. And the interaction between those ions, so a sodium ion, for example, would be attracted to the water, specifically the oxygen end of the water because it's got a partial negative charge. That's a new IMF of mixing. And very specifically, it's an ion dipole force. We can also have dipole-dipole. So that would be something like, let's say something like an alcohol. That's got a partial negative on the oxygen, a partial positive on the hydrogen, so it's going to be attracted to the corresponding partial positive end of the water through the oxygen and the oxygen end of the water through the hydrogen. I've also happened to illustrate hydrogen bonding, where both substances originally have hydrogen bonding, but then together they hydrogen bond. You can also have something like a molecule that just has a dipole that specifically involves oxygen, nitrogen, or fluorine. That oxygen atom in this molecule, since it has all those lone pairs of electrons, it can also hydrogen bond to water. Because when you have two different substances, you only need one of them to have the hydrogen actually bonded to the oxygen. The other one just has to have oxygen, nitrogen, or fluorine. And another thing that we looked at in the lab last week was things like alcohols. So let's say CH3, CH2OH, and water. Or the chain can get bigger and bigger. So this would be, that's ethanol. As my chain length gets bigger, they become less and less soluble. So this is propanol. This is butanol. This is definitely not just soluble, but miscible. Propanol is still slightly soluble. Butanol less or so. But by the time I get to hexanol, it's not soluble. And again, you should have seen this in the lab last week. This is because the hydrocarbon part is so much bigger than the OH. The London dispersion forces dominate, and these molecules like being together or you can think they like interacting with other hexanols via the LDF more than interacting with water. And so you need to be comfortable with making those kind of, or with those kind of ideas in terms of solubility. So these would all interact by hydrogen bonding, but there's also some dipole-induced dipole forces. With the hydrocarbon part. And again, that's usually not strong enough for the water. And so that's why hydrocarbons are usually not very soluble in water. In a case like that, you see a heterogeneous mixture. So for example, this could be the hexane, and this could be the water. And since the interaction between the two of them is not favorable for the water, they separate into two layers. So not good mixing at all. Let's quickly look at some of the kinds of questions we could ask about solubility in terms of predicting solubility. Since you can't really know without actually looking at the mixing whether something is going to be soluble in something or not, you can still compare two solutes and decide which one's going to be more soluble. So here we want to know which is likely to be more soluble in water. And we've got the methanol or the heptanol, and they're both going to have hydrogen bonding with the water, but there's going to be a significant amount of dispersion forces within the heptanol, so it's not going to want to break apart, and so the methanol is going to be more soluble in water. Same thing for these two, again in water, cyclohexane, which with water is just going to have the dipole on water inducing a dipole on the cyclohexane. That's not favorable for water. The tetrahydropyran, though, has both that dipole-induced dipole, which again isn't favorable for the water. But because we've got that oxygen, we also have some dipole-dipole forces. And so this one is likely to be more soluble. Still probably wouldn't be very soluble, but it's likely to be more soluble. Another term that I used that I should define is the term miscible. That's, write that again, M-I-S-C-I-B-L-E. That means soluble in any proportions. Which means that you can dissolve as much as you want of the solute in the solvent. And an example would be ethanol in water. I can just keep adding more and more ethanol, and it's always going to be soluble, so they are miscible. What else we're going to focus a lot of time on is looking at different concentration units, and it's going to be really important that you can go back and forth between the different units. So if you're given, say, molarity, to be able to go to one of these other definitions. And in general, concentration is a measure of how much solute is in a solution. And so there's different ways of expressing it just depending on what your application is going to be. And we already know the one that we're going to use the most, molarity. We learned that last quarter. It's a capital M, and it's the moles of your solute per the liter of your solution. So the reason we need something different from this is that volume is temperature dependent. So the volume of a solution can change depending on the temperature. And so we need a concentration unit that doesn't depend on temperature, and that is molality, which also starts with an M, and we give it the symbol a lowercase m. So make sure you're always drawing your uppercase m's very significantly different than the lowercase. This is also moles of solute, but now it's per the mass of the solution, so kilograms of solution. Another one that you might see a lot is parts per mass. So this is just what it sounds like. It's the mass of the solute over the mass of the solution. And these include ppm, parts per million, ppb, parts per billion, ppt, parts per trillion. You see those a lot in environmental applications, like how much of this type of contaminant is allowed in your drinking water. You can also have parts per volume, which is just in terms of volume. It's the volume of the solute over the volume of the solution. So you have to be specific as to which one you're looking at. And we can take those and easily turn them into percentages, and you've probably maybe seen at least percent by mass talked about in 124 or 127, and sometimes you'll see it labeled as like that, percent m/m. This is the mass of the solute over the mass of the solution times 100% to give you a percentage. And we can also have percent by volume, which would be percent V to B, and that's just the volume of the solute over the volume of the solution times 100%. And we'll use that in certain applications. The last one is mole fraction, and so it's just a fraction, which is the parts over the whole, so it's the moles of the solute over the moles of solute plus moles of solvent. And like I said, we'll do some sample calculations of that in class, and it's going to be important that you know how to use all of those and how to go back and forth between the two of them. I will always give you the definitions, but you're going to have to know what all of the different variables mean. So I think that's all I want to talk about. See you in class.